Yeah, I think a lot of people have heard me talk about this stuff in some shape or form before, so apologies for repetition. I have updated it a little bit since sort of last year. I presented it in San Diego. It's changed a bit since then. If you saw me talk about it at Woods Hole a couple of weeks ago, I have to admit that it's going to be quite a lot of repetition. It's not really been changed much since then, so you might want to get a cup of coffee or something if you fall into that category. But so I'll just cut to the chase. So we're interested in kind of trying to reconstruct the AMOC just from observations. Why do we want to do this? Well, there was a paper from Levka Caesar came out in about a month ago in Nature Geoscience, which sort of showed that there's a sort of coherence amongst the proxy records, suggesting that AMOC has weakened substantially over the last 100 years or so in comparison to the previous 2,000 years. That's based on things like ice cores and sediment cores, but not really so much based on actual ocean observations. And then the other thing is we have this Atlantic multidecadal oscillation, or Atlantic multidecadal variability, it gets called, in sea surface temperature, which is plotted on the right, which is this kind of 60 or 70 year apparent oscillation or variability that we see in the North Atlantic mean sea surface temperature. And there is some dispute in the literature over what's causing this sea surface temperature signal. Is it caused by external forcing? So some people are arguing that it can be recreated in models if you have carbon and then some aerosol forcing and then some carbon forcing again. Whereas other models suggest that actually it's kind of an internally forced thing. It's kind of some intrinsic property of the ocean that leads to this. And I think that's kind of the finger kind of points at the AMOC when they say that. And yeah, there was a paper by Michael Mann that came out in Science 2 or 3 weeks ago, which is on this topic, and it was kind of arguing this AMO pattern is actually a result of volcanic forcing. So in CMIP6 models, they saw that with volcanic forcing, you can recreate this this mode variability in the sea surface temperature. So what are we looking at? Well, we're looking just at all the available hydrographic observations from the North Atlantic that we could get our hands on. So, the North Atlantic was observed with increasing coverage throughout the last century. And the Met Office EN4 product is kind of, well, we lean quite heavily on that here. It's conveniently gridded all the T and S onto a 1 degree grid alongside their uncertainties. And these uncertainties account for the sparseness of the T and S fields, particularly in the kind of first half of the 20th century, when that's the issue is at its worst. We took the 50 degree north zonal section because that has the best coverage in the first part of the 20th century. So that's the black line here on the right. And the contours here, I'm showing color contours, are the mean sea surface height. So the idea is that on the 50 degree north section, we can compute the thermal wind, so the baroclinic component of the flow from the T and S from EN4. But and from 93 onwards, we reference that to sea surface slope from satellite altimetry. But before 1993, we don't have that luxury. So what we've turned to is this thing called the Bernoulli inverse, which is a method for generating a sea surface slope, which is dynamically consistent, basically with the general geostrophic flow. So it gives you a general geostrophic flow reference to the surface. Based on T and S. So I'm not really going to go into the details of how that works just due to time constraints. I'll just cut to the chase. So on the right here, this top right panel shows the Bernoulli inverse solution in blue and the satellite solution in black from 1993 till the present. And this is the sea surface slope. So this is d eta by dx along that line, if you like. So this is like surface geostrophic velocity. Yeah, so you can see we kind of, this is the mean over that time period. And you can see that there's a fairly good agreement in the overall structure. The blue kind of underestimates the the maximum here for the North Atlantic current and this minimum a bit, but it gave us enough faith that we thought, well, we could see what this gives us. So we can compute the velocity field as a function of x and z, and that's what these lower panels show. And the top one here is the velocity for when reference to the Bernoulli inverse solution, and the bottom one is the same shear but referenced now to the satellite altimetry solution. So you can see that we're kind of underestimating some of the baroclinic flow, but we're sort of interested to see how well it captures the overturning, essentially. It's just worth also saying that we impose net zero through flow on the 50° north section. So yeah, we calculate the overturning stream function just by accumulating transport through density layers. So this is what that looks like here on the top, and the blue now is the overturning stream function from the Bernoulli inverse, and black is from the satellite altimetry. And again, this is just from 1993 onwards. So this is when the two things coincide in time. And then we can define the AMOC as the maximum value at each time step of the overturning stream function, and plot that as a function of time, which we do down here. Again, blue is the Bernoulli inverse solution, and black is the satellite altimetry solution. The thin lines are monthly values, and the thick lines are annual mean values, and the correlation improves when we look at annual mean values. We kind of slightly underestimate the amplitude of the high frequency signal, but it improves as we look at the kind of low frequency signal. So we think really this tool is probably better for looking at low frequency, lower frequency variability. And also in red here, this is the rapid time series, which is obviously at a different latitude, but just added just for out of interest. The most prominent feature of the rapid time series is this step down in sort of 2007, 2008, and you could argue you see something similar, slightly as a slight precursor at 50° north in this time series. Anyway, so based on this blue line in comparison with the black line, we thought, well, it'd be interesting to see what the blue line does before 1993. So we did that just using all the way up to 1900, which is when the EN4 data starts. So what we get is something that looks like this now. So the AMOC, this is the AMOC anomaly at 50 north, based on the method I said. First thing to say is we don't really get a significant trend, although there is a large uncertainty, particularly in the first part of the record. So if we compare this to some of the proxy records, for instance, the Levka-Caesar proxy, it's qualitatively quite similar from like 1930 onwards, where we see that AMOC is high and then has a dip through its 60s, and then has another peak, which peaks around 2000, but not as high as the previous. This peak's not as high as the previous high in the 30s. The major disagreement with those proxy records, or with that particular proxy record especially, really comes before 1930. And that's when our, as you would imagine, that's when our uncertainties are at their largest. So yeah, I don't think we really can be too confident about what's going on there. But so yeah, although I see no significant trend, I don't want to claim that this is evidence that there isn't a trend. I think that'd be quite a controversial claim. I don't think I have the evidence to make it. What is interesting though is to compare this AMOC time series to the AMO, which is the sea surface temperature signal, which I talked about at the start, and that's plotted below here. So the AMOC is here in blue and the AMO is in red, and we do see quite a nice coherence, and there's a lag correlation peaking at 5 years. So the AMOC leads the AMO by 5 years, although that doesn't seem to be that consistent throughout the series, as you can see. So I'll just, what I did, this is at 50 degrees north, which is actually the best place to do it for a few reasons. And we decided on that after previously having done it at OSNAP. So since this is the OSNAP meeting, I'll show you what we did originally, which was we did it at the OSNAP section. And that's this time series here. The uncertainties are slightly bigger at OSNAP, but we still see a fairly similar pattern of variability where the AMOC seems coherent with the AMO in this lower panel and leads it. In this case, the AMOC leads the AMO by around 10 years rather than around 5 years. So, there might be some implications there, some interesting things to think about. But really what I'm doing now is focusing on 50 degrees north. So I'll summarize there. So what we've done, well, I'm not going to go over all this because I've already just said it, but I think to go back to the question of this AMO signal, the sea surface temperature signal, is it internally or externally forced? How does it address that? Well, we've seen evidence, I think, that the AMO is linked to the AMOC. Does that mean that the AMO is kind of internally forced and not externally forced? Well, I'm not really sold by this way of partitioning the two phenomena. I think it's convenient for numerical modelers, but in reality, the AMOC itself is an externally forced phenomenon anyway. And, there's the question of timescales as well. So, I think, I don't think it necessarily gives us a neat solution to that. But I think it's certainly evidence that the two phenomenon are coupled to some extent over these timescales. So I'll just end there, and I welcome any questions. Thank you very much.
Thank you, Neil. Any questions for Neil?
I can ask one. Neil, that was great. Thank you. Very interesting. So I'm going to probe you a little bit as to why you don't want to say that your study doesn't present evidence that the AMOC has slowed down over the last 120 years or 50. Yeah, 20.
Yeah, thanks. Yeah, well, I mean, so maybe it does, but I think really just because the uncertainties in the time series I'm showing now, the error bars do allow you to have a significant trend. You could add a trend onto that time series and stay within the error bars, and it would be comparable to the trends that's seen in some of the proxy records. So that's why really, and fundamentally this is because the errors, the uncertainty here, which is propagated directly through from the uncertainty in the TNS values in EN4, are just quite big, really. So I think that the errors are always going to be big here. It's why we need to do OSNAP. But it's still interesting that this pattern of variability emerges. I don't know. Maybe I should be a bit more forthright with claiming that I've got evidence here that the AMOC hasn't declined like the proxies say. But I don't know.
I have a question as well.
Go ahead.
Yeah, nice talk, Neil. I obviously did see your Hui talk, but I had a question that came up thinking about it later. So it's great that you represented it here. I don't have the AMO temperature pattern kind of in my head, but is it really I was wondering if the fact that they're correlated could be because of something more direct, your AMO kind of depends on the gradient of temperature across 50 north, right? So is that temperature gradient related to AMO as well? Does that make sense, what I'm asking?
Yes, it does. And I think that's, quite possibly. Yeah. And I mean, so, yeah, I mean, in some ways, these two time series aren't completely independent. The same temperature data is going to have gone into each of them. So, that's something kind of unavoidable. Maybe if we were doing lots of experiments in a numerical model, we could kind of account for that. But really, in my case, we were just trying to get all the possible data, throw it into the inverse and see what the AMOC says. And, it out-popped this pattern. I don't know how direct it would be. I mean, the AMO is a measure of a spatial mean surface temperature, and that can't impact geostrophy. Obviously, the AMO pattern might be associated with a spatially varying pattern, which can impact geostrophy, if you assume that these surface temperatures are representative of what's going on further down. So, Yes, basically the short answer to your question. Yeah, that's possible. So yeah, but in reality, you know, temperature and circulation are linked. So
yeah, thanks. I was just curious about your thoughts on that.
Yeah, so I think it's just unavoidable. But yeah, it's definitely worth bearing in mind.
Thanks.
Penny has a question as well. Sorry, Isabella. Penny raised her hand for a while. Go ahead, Penny.
Yeah, thanks. I just wanted to sort of echo what was said earlier about what the point that Fiamma made, really, that I think what you're showing, it does have quite a large spread. And so I can see your point about there conceivably being a, you know, ability to fit a trend line in there if you wanted to. But your pattern of variability matches incredibly closely with the same pattern of variability that Tom Rosby and his co-authors presented in his paper last year, which was using not EN4 or any gridded data set, but was using, you know, actual profiles and good quality profiles that they selected from north and south of the Greenland Scotland Ridge. So they also say that the evidence there from that analysis is of no trend in the AMOC over that 120-year period. So I think that what you're presenting is consistent with that, and so it's worth saying that it's consistent and that there isn't any evidence of a trend. I don't think you should shy away from saying it. That's all. Thanks.
Good. Yeah. Thanks, Penny. Yeah, I think that's. I'm glad you said that. Yeah, and I think the similarities or comparison with the Tom Rosby paper is definitely worth highlighting. So thank you.